Broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to our webinar, Best Practices for Maintaining and Monitoring Viscometer Chip Health. Today's webinar will be hosted by RioSense Principal Scientist, Dr. Stacy Elliott, along with RioSense Field Service Engineer, Damian Villapadua, and RioSense Engineer, Sid Kolhatkar. Today, they will be outlining some key points to consider in developing your strategy for chip maintenance, such as precautions to minimize the introduction of fibers or large particulates, cleaning solvents and protocol selection, including a demonstration of the RioSense automated chip cleaning station, and choosing and measuring NIST traceable Newtonian viscosity standards to assess health of your chips. Without further ado, I will turn it over to Dr. Elliott.
Hello, everyone. Thanks for joining. And as Eden said, we're going to be talking about chip health and how to maintain the chip health and how to monitor it. So once you put all your practices into place, which hopefully, the information we give you today will help you develop a strategy to do this, you'll need to monitor that and, ensure that you're doing things properly. I didn't catch whether Eden said it or not, but because we're live, we're going to try to take questions as they come in. Since we have multiple team members here. So if you have questions as we're going through, go ahead and don't wait to the end, go ahead and ask early on. So the first thing I wanted to start with is just sort of an overview of our technology so you can understand why maintaining the health of the system is so important. So I'm going to hand this over to Sid so he can get it closer to the camera. So this is the m-VROC technology, viscometer, rheometer on a chip. This is the microfluidics and MEMS. So you can see, I wanted you to visually see how small this is in scale. Thanks, Sid. And just to point out, the channel depth can be as small as 20 microns. So just as a reference point for that, a grain of sand tends to be about 60, 70 microns. So we're talking a fraction of the size of a grain of sand, the channel depth. So you can imagine that this, if you're not careful and you can easily get this clogged up, or even if it's not clogging, deposits over time are going to be relevant because they're going to be significant on that particular length scale. So that's why it's so important with the microfluidics to be very careful and keep things clean. So when we talk about chip, just in case you're not familiar with our technology, this unit here is what we refer to as the chip. And so that microfluidic flow channel, in addition to a electronics board and some fluidic adapters, are all encased in here. So it's in here to protect it. So this is what we mean by chip. And we have a slightly different version for all of our instrumentation. And today we're going to be mainly focusing on our m-VROC and our microVISC chips, and how we can, a lot of the things we're going to talk about it's still relevant in terms of dealing with our automated system, the Initium. But since we've recently done some webinar demonstrations on that Initium, we're trying to focus more on our other instruments today. So with that in mind, I first wanted to start off with some precautionary measures that you can take ahead of time and sort of during your sample prep situation. So the first thing is, as I mentioned, you want to be careful about fibers or dust that can actually get in there in your sample and then contaminate the chip. So it's always good to have either, if you're in a small space, compressed air such as this, or if you have a, house air or nitrogen system, and you can connect a, way to blow that out, then that will work well too. And you want to use that to blow out vials, blow off your syringe, any tools, just to ensure that there's no, fibers or dust there that can, contaminate the situation. Another thing is that, chem wipes are going to be off limits. I don't know if they market them as being fiberless, but our experience is that when customers use them, we see a lot of clogging with fibers. And later, when I guess Damian is talking, we can show you, how that can actually clog the chip. We'll show you some images. So we offer to our customers, and there's probably other suppliers of them as well, but we offer these lint-free wipes, which are superior to something like the chem wipe. And we find that they give off like very few fibers, if any. So that's another important thing to keep in mind. Something else when you're loading up your syringe to do the testing. And so this is going to be important for the m-VROC, not so much for the microVISC, because the pipettes are a little different, which you'll see. But because the tip is threaded, because this needs to go into, to be threaded into the entry point of the chip, if you load your sample up as is, so if you dip this into a vial and draw up your sample, then you're going to need to clean off this tip. And so even if you're using the lint-free wipes, the threading on here can shred the wipe and then introduce some fibers. So even if you blow it off, we find that just loading directly into the threaded tip can be difficult. So we recommend using an adapter, which is just very easy to put on. And then this way, this adapter can go into your sample vial, you can draw it up, and then you can take this off. And then it's just a matter of, dabbing the tip so that you don't use the threads to tear up fibers. So that's another recommendation. Okay, another one is, there's some controversy sometimes with whether do you filter your samples or do you not filter your samples, because then, if you're filtering your fully formulated sample, then there's the concern that you could lose, let's just say you have a protein solution, which is something we commonly work with. If you're filtering that, you may lose some of the protein to the filter, and also certain filters can have surfactants or other wetting agents that then might get into your sample. So, there's different schools of thought where, some people want to filter as little as possible because of those issues, and others are so concerned about particulates that they'll filter everything. So that kind of has to be, up to you. If you're dealing with very high quality, high grade solvents, and you're not dealing with particulate systems, then you may have less need to do this filtering. But if you do find it necessary to remove particles or fibers from your samples, if you have lower quality items there, more industrial grade, then it's very easy to use. You can easily buy many types of syringe filters, and you can very easily filter your sample in this way. So it just fits on the tip here. The ones we tend to use are either PTFE or nylon. They tend to be compatible with many different types of solvents that we deal with. And all the manufacturers of these will have tables that show you what the different materials are compatible with. So you can easily go in there and find something that will work for your system. And of course, they have a variety of different pore sizes. So, depending on what you might be filtering out, I think the lowest one we use is about 2.2 microns, and then up to maybe 1 or 2 microns. So this is an option too to help you, prevent any issues. Another thing you can do if you do have large aggregates, then you can also use a centrifuge to put those. So if you put it in a centrifuge tube, centrifuge it, the larger particles will go down to the bottom, and you can pull off the supernatant. And so we've done that. I'm not sure if you can see very well, but we made a guar gum solution, and it's a little tricky because we don't have a lot of lab equipment to get everything to go in solution. Plus, I think it's the nature of such a high molecular weight polymer. So you can see the large bottle here on the left. This is something, prior to centrifuging, you can see it's very hazy. And if you were to look close up, in person, you could see there were big particulate objects in there. So what we did was we centrifuged this for quite a while, maybe an hour or two, so that we got rid of all of the very large particulates, and now you can see we're left with something that's much more transparent, indicating that a lot of those large objects which would scatter the light are now gone. So centrifuging is also an option. If you are dealing with dispersions where you have particles, and then perhaps these particles can aggregate over time, and you do have the ability to do some complementary particle sizing measurements, like a dynamic light scattering, then we would recommend that so that you can be comfortable knowing what you actually have in there, and then that could guide you on whether or not you would need to filter, or if you were good to go as is. I'd also like to say that it kind of depends too on what type of particles you have. There's going to be a difference in behavior whether you have a hard sphere type particle versus a soft deformable particle, like we tend to consider proteins or antibodies kind of particulate-like, but obviously they're very soft and can deform. So hard spheres, of course, you have a more rigid structure there that doesn't deform, so you have to be a little more strict on your limitations on size. So typically we recommend not testing any samples that have particulates that are larger than 10% of the channel depth. So let's take our, I mentioned the smallest channel depth we have is 20 microns. So we don't want anything larger than 2 microns to go in there. And if you're dealing with the hard sphere type particles, I would say that's a very strict limit. However, if you are dealing with something that's more soft, like these proteins or antibodies, then there's a little more flexibility there because they can deform. But you don't want to go overboard there with that. But you can consider those to behave a little different. And then finally, once you have taken all these precautions, now you want to be ready to properly clean your flow channel after you do your testing. So you want to be prepared with the appropriate cleaning solvents so that you don't accidentally introduce something in there that's not appropriate. So you wouldn't want to, start your testing without being prepared to clean. Let's say you're running a protein or antibody solution and then accidentally try to clean it out with something like IPA, isopropyl alcohol. So that will denature those proteins, crash them out, and then quite potentially clog up your chip. So after you've taken all these precautions, you want to really be ready to clean out your system with the appropriate solvents. So let me just check my notes to make sure I got all the precautions listed out for you. I think I did. So now, now we want to move on to cleaning. Once you've taken these precautions to not contaminate your samples and your tools, now you want to decide how are you going to clean everything out. So now I'm going to turn it over to Damien, and he's going to start talking about everything cleaning.
Hi everyone, I'm Damien, the field service engineer here at RioSense. So I'm just gonna kind of walk you through just kind of cleaning your chips after measurements. So one thing I like to encourage, especially people who are kind of new to our technology, people to use is actually using these dummy chips. You can see here, it's pretty much that flow channel that Sid and Stacy showed earlier on, except it's on a microscope slide. So while you're testing your samples, you can actually just kind of start flushing solvent through it and see what's compatible, so you can help get a good cleaning out of your chip. All right, so close this and just kind of go over just tips on how to actually clean out your sample. So what we usually recommend is starting off with something that's compatible with your sample. So for like a protein, antibodies, samples, you usually use some type of buffer that's your sample will be in. So we'll just go ahead and flush that out with just your buffer right off the bat. And then for other samples like polymers, synthetic polymers, you can usually have those in organic solvent. So you would usually just filter it out with your organic solvent that's inside of it. So usually, depending on what you use, sometimes you can just leave it as that after you filter your samples, or after you push your cleaning solvents through the chip using the microVISC or m-VROC. But if you use something like a buffer, obviously the water will eventually start to dry out over time. So it can leave like those salts where it can start to crystallize a little bit. So to avoid that, we usually recommend cleaning with something else. So this can be something like 1% Aquet or some tween, just so that way you can filter out all the salts, and then you can leave the Aquet or tween in there in your chip, and that wouldn't be a problem. And then one thing you just want to make sure, it's you don't want to use something after your buffer cleaning that will be non-compatible with your sample. So this can be something like running IPA afterwards, that's something that can lead your sample to crashing out inside the chip, which can actually damage the chip. So it's just better to do something like buffer and then something like Aquet, so that way you have a good dilution to where whenever you run a sample next, it won't cause anything to crash out. And then just kind of extra tips, especially for people doing protein antibody formulations. We always recommend doing a enzymatic cleaning. So the two enzymatic cleanings we recommend is Turcozyme, which it would be around a 1% solution of it. And then a new one that we've been starting to use here is called Zymit Pro. So with Zymet Pro, you can use it at full concentration, and it's already in a solution, and you can pretty much use it whenever. With Turkizyme, it does have a lifespan about 3 hours before it'll start cannibalizing on itself. So as soon as it's made, you kind of have to use it right then and there. And then we'll just go a little bit more into other formulations you can use. So you can also use NaOH, usually 0.1 molar solution for protein antibodies formulations as well, and that will also help clean out your chip. I know everyone doesn't have all the same formulations, and most of these formulations are low in viscosity. So I'm just going to give a little bit more tips on high viscosity samples. So with high viscosity samples, usually if you do something very high and then you're using a cleaning solvent that's very low, this can lead to tunneling in the chip. So pretty much what that means is that as the sample is getting pushed out with your cleaning solvent, all the sample that's on the edges of the chip will sometimes just remain there, and it'll just create a tunnel where your cleaning solution will just pass through without removing anything on the walls. So what we recommend is we can doing kind of like a step down. So you can use your cleaning solvent and dilute it a little bit into your actual sample if you have plenty of it. So that way it kind of works as an intermittent step to where it'll clean everything off the walls while still having your cleaning solvent. So the next time you just run your pure cleaning solvent through, you should be able to wash everything through. And if that's still not if you're still kind of noticing like higher viscosity readings or like some kind of a tunneling effect, you usually can try heating your sample up. For pretty much almost all samples, if you heat up your sample using either temperature thermocube for the m-VROC or our temperature controller for the microVISC, it'll usually cause the viscosity to go down. So that way it makes it easier for the cleaning solvent to actually push out your remaining sample. Or you could also just try leaving cleaning solution inside of your chip, so that way it just soaks up and then it's able to have a little bit more interaction cleaning out that solution. And then whenever you are doing these cleaning cycles, you're pretty much going to be running them just like you're running any normal sample. So for m-VROC, we actually have a cleaning cycle. So you would just load a pipette with your cleaning solution, put it back onto the microVISC, and then you would just scroll down and you'll using these arrows, and there should be one that says cleaning mode. So that should push the syringe all the way through at a low flow rate just to reduce any chances of overpressuring occurring. And then with m-VROC, kind of the same procedure. So we'll load up a syringe full of our cleaning solvent, hook it up to the chip in m-VROC, and then we'll just set a low flow rate to run at, so that way it doesn't risk overpressure with the chip. All right, and then so those are kind of the ways for manual cleaning. So I'm just going to talk a little bit more about the automatic, kind of like the set it forget it method that we've recently been starting to release, which is using this over here, which is the chip cleaning station. So with this chip cleaning station, we have 3 solvents connected to it. So essentially, I'm kind of going back to what I said. We have that primary, which would usually be like your buffer or some type of organic solvent, just depending on what you're working with. And then we'll kind of have Sequet. So that'll kind of just be that last step to where you can flush out your buffer. And then we have a we call this an enhancer. So what it does, it's usually a volatile solution, so that way we can actually dry out your chip in the next step, where this will actually dry out your chip completely, as long as you have all of these set up correctly. So after you're done measuring for the day, all you would have to do is just kind of pop out your chip, and then you can just put it right here, and then connect it using either this adapter for your microVISC, or you would just disconnect this adapter, and you're ready for your m-VROC. And then all you would do next is just set it on right here where the chip connector is. And then depending on the protocol, you would just click start, and then it'll just run through that cleaning for you. And then you don't have to worry about any of the syringes doing that. All right, so we do kind of have a few examples of chips of what happens like when they're not being cleaned properly. or if you're kind of just letting fibers kind of get introduced. So let me go ahead and pull those up. All right, 1 second.
Hey, while you pull that up, Damien, we have a quick question.
Sure.
So what is the cleaning cycle used in the cleaning station?
So
and then there's a drying step. So when does the drying step happen?
okay, so for the chip cleaning station, these 3 solvents, it's totally dependent on what you're actually measuring. So if you're measuring like a protein antibody solution, this would be your buffer. This would be your equette to remove the buffer, and then this would be either acetone or IPA, something volatile. So that way, when we do dry, it's a lot easier to dry out IPA or something like acetone compared to drying out equette, which is a 1% solution with water. So after it runs through these 3 bottles in order, and after it's finished with the enhancer step, which is your volatile liquid, they'll start drying it. So we'll just pressurize these bottles and then just allow air to flow through. And then after a certain amount of time, depending on what you're cleaning out, you can set how long it dries. And then after that, they'll just finish drying, and then you have a dry chip, and you can just store that away without worrying of any extra liquid being left over after your measurements. All right, so let me go ahead and share my screen. All right. So if you can see right here, and so this is a close-up picture of the MEMS chip. So from here you can see like these leftover residue and just from improper cleaning. So this usually occurs whenever either your cleaning solvent is not actually cleaning out your solvent or out your sample, or it's just an immiscible comparison, or you're just leaving your sample without cleaning for the day as well. So this usually, if you run a sample and if you don't do any cleaning steps after, and after like 1 day, will usually cause your sample to like just solidify, or like the solution will evaporate, and you're kind of just left over with this. And then if you try to run again, you'll usually notice right away by either getting like an overpressure warning, or you'll also get a incorrect data. So if you were running something like water, instead of getting around the 0.9 to 1 CP, you'll usually get something higher, like maybe 1.5 or 2 CP. All right, and so this is just from cleaning alone, and then I have another one for oh, here it is. And then going back to what Stacy was saying, is just being careful with fibers entering your chip. So once a fiber actually enters your chip, because we're dealing with like microns of depth, we're not able to get this out. So even though like it looks pretty clean except for this fiber, that fiber is in there forever, and we'll have to like replace the chip for you. All right, and then if you guys have any more questions about cleaning, go ahead and ask, and we'll be monitoring those questions. And then without further ado, I'll kind of let Sid take over on how to actually monitor the health of your chip.
Hello, my name is Sid, and as Damien said, I'll be going over the monitoring your chip health. So where do we start? So the first thing we start with is the NIST traceable oils. So what is NIST? So NIST stands for National Institute of Standards and Technology. It's basically an agency that provides a framework for giving accurate measurements. So they provide various tools that they qualify. They provide various standard reference materials, which have defined fluid properties, and they provide certification of analysis for that. So there's a lot of different standards. We have oils, we have silicon standards. Oils are the ones that we prefer for a few reasons. Primarily, oils are not very volatile. They last a long time, and they're easier to clean out of our chips. Some people use silicon. These are not incompatible with a lot of different samples, and they're a lot harder to clean. I know some scientists will prefer to use glycerol water mixture that they may have in their cabinets, but as this mixture is hygroscopic, it can absorb moisture from the air, and that would kind of change the nature of your fluid and its properties, and we want to keep these as constant and traceable as possible. So which oil do we choose when we're running through our samples? So whenever we have a chip with a lower pressure range or a smaller width, we will use an oil that has a low viscosity. So for example, let me show you our kind of sizing standards. So if I go here, you can see that our A chips, which have the smallest pressure ranges, we use a relatively low viscous sample oil, like an N2, which has a viscosity of approximately 2. As we increase the channel depth to A20, A30 chips, we go with the higher viscosity oil. And as we switch to B chips and C chips, we can see that we increase the viscosity of the standards that we're using. So with each of these oils, there's many different types of oils. We have N2, N10, N140. These all have different viscosities and different properties. When we get these from NIST, we get a certificate of analysis, which looks like this. Here you can see it comes with the name of the standard, when it was issued and the expiry date, as well as the various viscosities at different temperatures. So one thing to keep in mind when we're doing these NIST traceable standards is to make sure that the oil that you're using is not expired, because as the certificate of analysis will only qualify for a certain amount of time. And the other thing to consider is the temperature. So looking at this certificate, we can see that there's different temperatures, and each temperature has a corresponding viscosity. We know that viscosity is very dependent on temperature. So when we're using our NIST oil for our testing, we want to make sure that the temperature that we're using falls within this range. And when we're trying to figure out what our reference value is going to be for the viscosity of the oil, we should use an Arrhenius model interpolation to get the correct viscosity at the correct temperature. So how often do we do this NIST traceable testing? So that depends on the application that you're going to be running. If you're using this system to be qualifying some other process or some other sample, then this should be done very often. You should be doing it at the start of the day to make sure the chip is in good condition, and then at the end of the day to make sure that the data that you collected throughout the day was accurate. If this is an application where you're just looking for some research, you're trying to characterize some fluids for your own research, then it doesn't have to be as aggressive of testing. So perhaps every other day or once a week would also be acceptable.
And then I have a quick question.
Sure.
So pretty much the question is, can we run oil and then water after, or like what solvent would you run after running an oil standard?
For sure, yeah. So with oils, we will generally run heptane or IPA, and I'll get into that a little bit further when we do our demo. Oil, because oil and water generally don't mix, using a water sample to clean out your chip won't work as well as we'd like. So let's start by running a sample on the microVISC. So we have 2 stations here loaded, and maybe I'll back up the camera so we can see both stations. So we have the microVISC here, and I have it loaded with A05 chip. And then this one, we have the m-VROC loaded with the B10 chip. So going to the document that shows, so we can see that for an A05 chip, we're going to be using an N2 standard. So that's what I have loaded right here. So what we're going to do is I'm going to open the program. So this is our microVISC control program. Here I've given it the name of the oil that we're going to be using. Here we can see the temperature that the system is currently at. So when I set the automatic feature on the microVISC, it's going to give us a pressure range that's around 50% full scale. Oh, is there a question?
Yeah, so I have a question. So they're asking if the calibration sheet says N7.5 and it is recommended to use N10. Are these good chips? Are these good choices for the chips? Is one better than the other, or does it depend on the samples you are running? I can go ahead and answer that one.
Sure.
So depending on the instrument, we use different oil standards. So if you have a microVISC, I believe we use either N7.5 or N10, and that's just because with the microVISC, it has a lower flow rate compared to the m-VROC. With m-VROC, you're able to reach higher flow rate and shear rate, so that's why we can use a little bit of a lower viscosity standard like N2. But any of these choices are still good and valid for running on the chip. These are just ones we use for our internal calibration process of these chips.
Thanks, Damien. So going back to the microVISC system, I am going to run the sample, and then we'll take a look at what the data looks like. So first, it's going to do a baseline measurement. All right, now it's priming the chip, so it's just filling the chip with fluid. Great, so we got some data here. So we can see that the temperature that it was run at was 21.21 degrees, and the viscosity of the sample was 2.157. So now we have to go and compare this with our certificate of analysis for the N2 chip. So this is for the N35. So there is a similar certificate for the N2. The way we calculate it is here we have done the Arrhenius interpolation. So we can see here I would input the temperature we just got, and it would output a viscosity that it should be for this temperature. So the published value is 2.147. Our calculated value is 2.157. Our chips are accurate to under 2%. So we can see by doing a percent error calculation that this would fall under the 2% threshold. So this is a good chip. So once we've completed testing the oil, getting the correct measurement, the next step would be to clean it. So for this particular chip, I'm actually going to load it on the chip cleaning station so we can see what that looks like. And I'll move on to the m-VROC system, and we'll do a similar procedure with the m-VROC. So if you just want to change presenter to number 2. Okay, perfect. So this is what our m-VROC control program looks like. So as I mentioned before, for this chip, this is a B10 chip. We're going to be using an N35 standard. So similar here, I'm going to input the sample ID N35. We're going to get an estimated viscosity that I'm going to put in. This is based on the published values from the certificate of analysis. And this gives us a good flow rate that we can use between. Yes.
All right, I have another question. So how do you do that calculation? I'm assuming the one where when you change the temperature, it outputs the viscosity for that temperature.
Mm-hmm.
And then did you also say erroneous earlier?
Arrhenius, yes. So it was the Arrhenius model of interpolation.
Yeah,
Stacey can
sure.
speak a little more about that, I'm sure.
So if anyone's familiar with, let me just
You can trade spots.
familiar with reaction kinetics, where you have the Arrhenius law for reaction constants. Viscosity as a function of temperature for many fluids will follow the same type of relationship. So it's basically viscosity is exponential of some activation energy divided by kT or RT. So that's the relationship that we use because that works well for the fairly simple mineral oils that we have here. So that's the equations that are used, so you can search that up. Also, if for our demonstration we didn't bring in our temperature control because it would just introduce much more noise and make it a little more confusing. But if you are using our temperature control for either the microVISC or the m-VROC, then you can just set the temperature to be at one of the values that's actually on the certificate of analysis, and then you wouldn't have to do any interpolation at all. It's just if you don't have the temperature controller or you happen not to be using it, then you can still check your oil and do the interpolation. But if you are using temperature control, then it may not be necessary. While I'm here, I'm going to get my props out of the way so that we can be ready to run the chip cleaning station.
Thank you, Stacey. Okay, let me move this a little bit. Okay, so here I have already loaded the N35 oil. You can see it right here. One thing I forgot to mention actually, when we're running these NIST traceable oils, we should be running them similar to the pressure scale that you'd be running your experiments at. Now, for the sake of simplicity for the microVISC, I ran it in auto mode, which generally sets it to 50% of the full scale. However, if you're running experiments where you're going all the way down to 5% full scale, so lower flow rates, or 95% full scale, higher flow rates, then we recommend running the sugar rates for that as well. As these are Newtonian samples, the viscosity should be same throughout, but it's good to get full range of the chip to make sure that the chip is good at all levels of your pressure scales. Here, coming back to the minimum flow rate and maximum flow rates, I'm going to pick something that's in the middle to get that 50% full scale. But if you're running, again, experiments at lower or higher flow rates, then I would recommend running them at that speed as well. I've just set a time of 10 seconds and a measurement time of 10 seconds just for getting good data. So we'll go ahead and start that. So this is going to give a similar result. We're going to get a temperature reading as well as a viscosity reading. And then we would compare that with the Arrhenius interpolation from before, and just to make sure that our chip falls within that 2% accuracy. Damien, could you do me a favor and could you change the presenter back to this computer? I wanted to show the cleaning procedure. I don't know if it's seeing what I think it's seeing.
You didn't get it pop up?
No. Oh, yes, now I did. Thank you. So once we're done with the measuring the oils and we've got data where the viscosity is within 2%, it's validated that our chip is healthy, not clogged. The next thing we do is look at how to clean out the oils out of these chips. So specifically with the m-VROC, we can see that for different oils, we use different types of solvents to clean out the chips. Adding on to what Damien was saying earlier, if we're using a oil that is very, very viscous, like the N1400 and the N4000, we recommend running a mixture of the heptane as well as the oil itself so that we avoid any of that tunneling effect. So for the sake of this test, we have an N35 oil, so we're going to be using heptane and IPA as our two solvents to clean out the chips. We like to run, 2 milliliters of the heptane and then about 1 milliliter of the IPA to make sure that the chip is totally clean. So I'll go ahead and I'll load the heptane into the m-VROC now. So we start by moving the pusher block out of the way, opening up the jacket, closing the chip. Is that a little earthquake?
A little excitement.
I remember moving to California. I'd never experienced this before, and the first time was definitely very scary. It's just so unexpected. So I'm loading the heptane. Yeah, now it doesn't phase.
Now you have a recording of one of your first earthquakes.
Yeah, calm, cool, collected. So this is the heptane. We'll open the chip, close this off, and we'll push the pusher blocker nice and close. One more time, could you switch over to this computer?
Yeah.
Great, thank you. So I'm just going to pick a relatively low flow rate. Because I know this is not a very viscous sample, I just want to slowly push out all the oil that's in the chip. And I'm going to set a very long measurement and pause time just so it goes through a lot of the fluid. So we can go something like 200. Oops. And there we have it. Now it's just going to run through the heptane. Once the heptane is done, I will swap it in with the IPA that I preloaded, and then I'll run it through the chip. And that's how we ensure that the chip is clean of any of the NIST oils.
So while that's running, I have a question. I think Stacy might be able to help out with this one. So if you're running M35 at an ultra high shear rate, viscosity will decrease from m-VROC results, and standard oil is Newtonian, so it shouldn't present any shear thinning. What kind of factors do you think is kind of influencing the result? So to kind of repeat the question, if you're running a standard and at very high shear rates, you notice a decrease in it, what do you think are some factors that might cause that?
So it could be an issue with the chip. So if, when we calibrate these, we do a pressure calibration across the range from 5 to 95%. But over time, if something happens, perhaps, that could start to fail. So that's one option. Another option is really depending on how high in rate you're going and what the channel dimensions are. It could be viscous heating. That's potential. I don't remember the equations off the top of my head, but there's a way to estimate, whether that could be happening based on the shear stress and the shear rate that you're operating at, and also the thermal conductivity of the oil. So viscous heating could be an issue there, because as we talked about earlier, as you increase the temperature for these oils, which behave pretty simply, the viscosity will go down. So those are two of the possibilities.
Hey, Stacey.
Great. So the last thing I'll do is I will load the microVISC chip into the chip cleaning station, and then Damien can maybe show how to run it. And then we'll open it up for final questions. So for the microVISC, and I should have brought it closer before doing it, we have to install this adapter so that the channel can connect correctly to the input of the chip, and then we set our catch waste bucket here just so we don't drain any of the liquid all over our lab bench.
All right, and let me just stop sharing the screen for a little bit of a better view. All right, so let me kind of just move this a little bit over. So essentially, you can make your own protocols, and all you're doing when you're making protocols is just controlling the time in which you're dispensing your solvents, and then towards the end it'll actually dry. So we already have a pre-made one specifically used for oil, to where we just kind of flush it through with IPA and heptane, and then just allow it to dry afterwards. So for the sake of not making a lot of noise, what we would do is just press start, and then it would just start running some pre-run checks to make sure that these balls aren't leaking, and then it would start going through your solvent. But yeah, that's pretty much how you'd use the CCS. If you have any questions about CCS, you can go ahead and feel free to shoot us an email, as well as if you do already have one, we can kind of also go over some kind of best practice way to kind of make your own protocol as well. All right.
All right, so I think that pretty much covers all the planned content that we had. We took some of the questions as we went along, but we'll wait a couple more moments here to see if there are any questions that come in at the end. Anyone, just while we're waiting to see if more questions come in, as we always do, we will send out a recording of the webinar to anyone who signed up, even if you weren't able to attend. So if you wanted to go through it again and have questions later, and reach out to our team here, we'd be happy to help you out. But it looks like maybe we did get a question.
Yeah, so we have one question, and the question is, how long does it take for the chip cleaning station to run? So with the chip cleaning station, it's all dependent on what chip you have. So today we ran an A05 chip, which is one of our most sensitive chips. So these take a little bit longer to clean, just because we don't want to risk overpressuring the chip. But so this can be anywhere from 10 to 20 minutes, just depending on what type of cleaning you want to do and if you want to dry it at the end. For other chips like B05 chips, all the way up to our E chips, these are a lot faster, just because we're able to flow solvent to the chip more quickly than with the A chips. Yeah, hope that answers your question.
Another question for you, Damien. Mm-hmm. So what are some causes of deviation so we can troubleshoot any chip health issues if the chip is reading too low consistently or too high?
So the best thing to do if you're questioning kind of what's going on with your chip, I always recommend picking some Newtonian sample. So this could be something like water. If you have any standards like a glycerol standard, an m-VROC standard, or an oil standard, and I would just try to run it at multiple shear rates. So usually with multiple shear rates, you're able to check to see if there's anything going on with it, because the sample is Newtonian, it should be the same viscosity across all the shear rates. So if you know any deviation, so like let's say it kind of slowly creeps upward as you're running at higher shear rates, you can usually suspect that there might be something inside your flow channel, or you might just need to do some type of enzymatic cleaning if you're working with protein samples like that.
Great,
All right.
thank you.
Yep. Do you have any more questions?
No more questions, but if you guys think of additional questions later, as Damien said earlier, you can just email us and we would be happy to help.
Okay, great. Thanks everyone for joining us. And if you're in the United States, I hope next week is Thanksgiving. So have a happy Thanksgiving, and we'll be back again in December, as we always do. Come to you monthly. Okay, thank you.